As things get really small, things also get really weird. Quantum superposition is evidence of that weirdness. Superposition is when something is placed above or upon something else. A quantum state, simply, is the location and behavior of a microscopic particle. Quantum superposition, then, is when two or more quantum states can be added together or placed on top of each other to make another equally valid quantum state that applies to the particle. One particle is associated with at least two states, the most basic being two opposite forces, upward or downward spin, for example. These states can be superposed, creating a new quantum state that is both upward and downward that the particle is still associated with. These states can be superposed in different proportions, being either more up and less down, or vice versa. A microscopic particle, then, can theoretically be in an infinite number of places and behave in an infinite number of ways at one time, since we can constantly add different proportions of quantum states together to achieve more and more quantum states that apply to that same particle, which is superposition. The phenomenon of superposition can be deduced by various experiments. The double-slit experiment, devised by Thomas Young, for example, makes a single line of photons pass through the two slits and onto a photosensitive surface. The photon is the particle, while its wave behavior and position is the quantum state. Now, when we observe the photosensitive surface at the end of the experiment, we see rows of light and dark stripes. This shows interference waves. The dark stripes are where troughs of the waves undergo destructive interference with the crests of another, canceling out the wave peaks, and thus no light is received. The light stripes are where the photons are. In other words, they're where the crests of the waves undergo constructive interference with each other, and the troughs of the waves undergo constructive interference with each other, reinforcing the wave peaks. However, note that it's a single line of photons. In other words, only one photon at a time is emitted, and we only send another photon once the previous one hits the photosensitive surface. How then is the photon a single wave thanks to its properties, showing interference patterns of multiple waves? The only way is if the photon interferes with itself. A superposed photon that is a combination of the two slit positions in two different wave patterns goes through both slits at the same time, and creates two waves that then interfere with each other. Even though we can view the effects of quantum superposition, the interference pattern of an individual superposed photon, for example, we can't physically observe quantum superposition. In the double-slit experiment, for example, if a photon detector is set up, the results are vastly different. Each slit is followed by a band of light, rather than the interference pattern of superposed photons. It's as if the photon knows it's being measured. The attempt to measure the superposition has destroyed it, forcing the photon to transition from a superposed dual-wave particle photon into a particle with a fixed position, one of the two open slits. This is known as decoherence. When we attempt to measure or observe superposition, the superposition disappears, limiting the particle to a specific location and behavior, and destroying its ability to interfere with itself, just like how we don't know the height or position of a wave in the ocean until we measure it. We call this collapsing of the superposition. The particles go from quantum to classical physical behavior, the motion of bodies or forces based on Newton's principles. The act of measurement solidifies the situation from an undetermined form into a single state, and a physical reality takes over the superposition. The concepts of quantum superposition and decoherence then raise many more questions. At what point do quantum mechanics stop and classical physics take over? This led to the famous thought experiment of Schrödinger's cat. Schrödinger's cat involves a cat locked up in a steel pen, where its life depends on a radioactive atom on a Geiger counter that has an equal chance of breaking down and not breaking down. If not, the cat lives. If it does, a chain reaction occurs and a flask of hydrocyanic acid explodes, killing the cat. Quantum superposition states that while the cat is still in the steel pen, it is both alive and dead. It can only become one or the other once we check the result. However, we know that the cat can't possibly be both alive and dead. It can either be alive or dead. This experiment sort of pokes fun at this interpretation of quantum superposition, which we call the Copenhagen interpretation, and questions the point at which reality takes over superposition. And when does that occur? No one knows yet. We're not sure why quantum superposition disappears when it's measured, or at what point something stops being able to be quantumly superposed. But it has led to some interesting theories. For example, the multiverse theory that each particle is in every possible configuration or position in an infinite number of different universes, and the interference pattern mentioned earlier is one photon from one universe interacting with one from another. Thus, according to multiverse theory, the cat in the thought experiment is both alive and dead, just in different universes. However, only one of those possibilities manifests itself in our universe. Just remember, the next time you think you got a bad grade, just never look at the test or measure it. It'll remain forever in a state of every possible grade, though that's not really how it works.